Hello students, this is class number 2 for hydraulic engineering on January 11th, 2018. We'll begin with a couple of announcements here. Please remember to upload your introductory assignment before 3:30 p.m. on Friday the 12th. Since this recorded lecture is meant for Thursday, that still gives you a little more time to finish the assignment before it vanishes on MU Online. Also, your first real assignment having to do with calculations and flow resistance and related ideas, that's due on Tuesday the 16th. So please be sure that you upload that assignment to MU Online before our class time, 3:30 on that Tuesday. And let me know if you have any questions. I'll be responding to email over the weekend and while I'm down in Clemson, so please just let me know if there's anything I can help you with. Today's lecture is covering flow resistance, which is chapters 7.1 through 7.3, and also covers some of the ideas behind flow type and velocity distributions, and that's in sections 4 and 5 of chapter 7. The majority of this lecture was recorded during a previous semester, so as always there may be some casual references to time that may not match up, but be assured that any announcements that are on this slide are the ones that govern, and you can ignore any announcements about due dates or that sort of thing that may be casually mentioned during the lecture itself. With that said, please again let me know if you have any questions on the material, and I'll see you in class on Tuesday.
You all, I hope, remember a piezometer. And a piezometer is a way of measuring pressure. And remember, if the piezometer wasn't there and we punctured the pipe with a hole, then water would just spray all over the place. And the higher the pressure is, the faster it would spray out of the hole. But if, instead of just puncturing with a hole, if we punctured it with a tube, like is shown there, the water level will rise in the tube to a height that's determined by how pressurized the pipe is. Now, in this particular drawing, the pipe is inclined at the slope S0. S0 means either the slope of the pipe in the case of closed conduit flow, or if it's a river or a canal or any kind of an open channel, then it's the slope of the bottom of that channel. Okay, so it's a physical slope. The slope of the energy grade line, the hydraulic grade line, by contrast, is if we connected the dots of those two water heights, the columns there. Now there's a little dashed line there, but that dashed line that's on there is a horizontal line. And the reason why they put that horizontal line in is just to make the point that at the downstream piezometer, the water level, it's not as high as that horizontal line. That actually there's an energy loss denoted HF, which means energy loss due to pipe friction. That's why the water level is a little bit lower at the downstream piezometer, is because of pipe friction. It's due to the resistance imparted from the pipe to the flow as the flow is moving towards the right. So any questions so far about what we see here? All right, you remember the last time I said in class that the slope of the energy grade line, S sub F, is what we term slope of EGL or HGL. I use them interchangeably, and oftentimes that's okay. If the pipe diameter isn't changing, then they have the same slope. If the pipe diameter changes, then remember that the EGL and the HGL can diverge. But strictly speaking, what we're seeing here, the water height is rising to the HGL, the hydraulic grade line. If we had a little tube that was doing this, then the water level would rise to the EGL. Anybody remember why that is? Why a tube that's facing the flow could trace the EGL for us? How are EGL and HGL different? What are the three terms that goes in? Exactly right. Yeah, it's the velocity term, because the EGL is pressure head, elevation, and V squared divided by 2G. Whereas if we want to draw the HGL, what we are going to graph is just the pressure head and the elevation without the velocity. And so, if these two tubes are really close together, I've got one of them directed into the flow and one of them not, then the water level would be a little bit lower down here, and then the gap between them would be v squared divided by 2g. You know, that difference between EGL and HGL is the velocity head. Okay, so that aside, the main thing we want to look at here is that this is a way for us to visually see the effect of pipe friction. It's not just some abstract thing that you can't measure. It's hard to think about shear stress, you know, a shear stress field in the fluid. But you can actually measure with the pressure gauge, the pressure decreasing. That's an effect of shear stress that you can measure. You can see the piezometer, the water level is going down. And that's a reflection of the decreasing pressure. So HGL is the pressure head and the elevation head. And so here is the change in HGL. This is the change in elevation of that line from one piezometer to the other. And what we're saying is that's the energy loss. That is H sub F. So if that change in elevation is the head loss, the right-hand term, this is the Darcy-Weisbach equation. F L v squared divided by d2g. Darcy-Weisbach equation. Here it is again. What it says is that the amount of head loss that you have between 2 points can be calculated based on the length. And so since this is in the numerator, the L is in the numerator, that means the further apart 2 points are, the greater the energy loss due to pipe friction is going to be. So if you have this 10 meters apart, then you'll maybe have some HF. If you had it 20 meters apart, you'd have double the energy loss. Velocity, though, isn't directly proportional. You see that velocity squared. And so if you double the velocity, then you'll have 4 times as much energy loss due to pipe friction. Diameter of the pipe is in the denominator, meaning that if you have a small pipe, what effect is that going to have on the energy loss? It's going to have a lot of energy loss, actually for 2 reasons. Because a smaller pipe is going to increase the velocity, so that's the indirect effect of the small pipe. But directly, what it does is when you have a small pipe, think about how far away are you getting from where the resistance is. In a big pipe, you know, all this flow is pretty far away from that edge of the pipe wall that's imparting resistance. Whereas when you've got a small diameter pipe, the entire cross-section is in pretty close proximity to that perimeter where the pipe is holding back the movements of the liquid. So that's a little exploration. And of course, F, we talked about last time, that's the friction factor that we can look up from a Moody diagram, for example. And it's calculated based on the flow conditions, because along the horizontal axis of the Moody diagram is the Reynolds number. And then it's also a function of the relative roughness, which is the equivalent sand roughness of the pipe relative to the pipe diameter. So Darcy-Weisbach equation, really important. We're going to use it a lot this semester. Just a reminder, I mentioned it before, that the 2 slopes that we've got here, the slope of the pipe, S naught, and if we draw a little dashed line connecting the dots of the HGL, if we had another line that's going from here to here, and I'd be delighted if you drew that line on your tiny little drawing, that would be the HGL. The slope of that line is not the same as S naught. It's just coincidental. If we made this pipe horizontal, for example, if we flattened it out, then S sub F would stay the same. It wouldn't all of a sudden go flat. You'd still have the same amount of energy loss if the pipe is horizontal, or if it's upward inclined, downward inclined. The energy loss is not affected by the pipe orientation. It's affected by length, velocity, diameter, friction factor. There's no term in the Darcy-Weisbach equation that asks what's the slope of the pipe, the physical slope of the pipe, because it doesn't have an effect. The 2 are independent. So, any questions or remarks about that? All right. There's one of your homework problems that asks you to calculate or use the shear velocity in a calculation. And shear velocity, as it's described in your textbook, has the variable V star. And what it is basically is a way to express shear stress with units of velocity. So it's just rearranging the shear stress expression, which we already had, and substituting that into the Darcy-Weisbach equation. So if we're combining these two together, then one thing we remember is that for a pipe that's flowing full, the hydraulic radius R is diameter divided by 4 when the pipe is full. And so if you combine those together, it may not immediately be obvious where that 8 is coming from, for example. See the 8 that's here? Well, it's because we had 2 here, and then the radius we're substituting d divided by 4. So trust me, it works out when you combine the two together. You end up with a relationship between the shear stress and the friction factor, F. And so it tells us that the friction factor and the shear stress are directly proportional. Now, if we rearrange it further, if we rearrange the shear stress that experienced by the fluid divided by the density of the fluid, we just look at the units for a second there. The shear stress is newtons per square meter. And then if we have density in the denominator, and that's kilograms per meter. And so if we expand out what newtons are, that's a kilogram meter per second squared. And then we still have the meter squared from before that was in the denominator of the shear stress. And here's meters cubed per kilogram, which is the inverse of density units. Combine it all together, cancel out the terms, and you've got meter squared per second squared. And that's what we call the shear velocity squared. So this is just, we've rearranged it intentionally so that when we take the square root of the shear stress divided by the density, like here, then it ends up having units of meters per second. So it's a way of describing the shear stress in a flow field. And when you need to use it in the homework, this is an expression that may be useful. What it says is that if you know the flow velocity V, then you can calculate the shear velocity V star as a function of the friction factor F. So just maybe put a little star next to this one because it'll come in useful as you work through the homework problems. So we've talked about pipes mostly. Let's briefly talk about open channels, even though we really won't get into it until the second half of the semester. Here's a trapezoidal channel, and the geometry of a trapezoidal channel is a little bit more complicated than it is for a rectangular channel. A rectangular channel is nice and easy because, for example, what is the cross-sectional area of a rectangular channel? Well, the area is just the bottom width times the depth. That's easy enough. And what about the wetted perimeter of this rectangular channel? It would be 2 times the depth plus b. So we like rectangular channels because the geometry is just open and shut. On a trapezoidal channel, it's a little bit more tricky because as you can see there, we've got these side slopes. And the way that we define the side slopes is there's some horizontal component to the slope and a vertical component to the slope. And so in the textbook, what they do is they say, let's make that a ratio where the vertical component of the slope is 1, and then t tells you what the horizontal component is. So if it is t equals 2, then that means the horizontal component has 2 units for every 1 unit vertical. So for t equals 2, that would mean, let's just say hypothetically that the depth is 1. If this is 1, then that would mean that that is 2 for t equals 2. So what's going to be your approach to calculating the cross-sectional area? Any guesses? Take a stab at. Okay. So you do the average of these. Okay, yeah, that could work. What's another approach? Okay, what would the shapes that you'd make? Two triangles and a rectangle. That's what I usually do. I hadn't thought of it that way, thinking outside the box. Yeah, so we'll go through that today. We'll calculate the area and the wetted perimeter. When we do, it's important to mention that the flow resistance parameters are the same as they are in a closed conduit. That you've seen this relationship before, that the shear stress can be calculated by the fluid unit weight, gamma, the hydraulic radius, and the slope of the energy grade line, S sub f. So here's another example where you're going to have a homework problem that you need to substitute in the definition for the hydraulic radius. And I think what they do in that problem is they tell you the shear stress, they tell you the slope of the energy grade line, or not directly. I think they tell you the head loss and some distance. So you have to calculate S sub f. But, given, easily calculated, and then the hard thing is calculating some parameter of the geometry of the channel. So let's do that. Let's look at the area and hydraulic radius and wetted perimeter for a trapezoidal channel. All right, so what is the hydraulic radius for a trapezoidal channel in terms of B and Y? B is the lowercase b is the bottom width. Capital B, in some text it's assigned the variable t to mean top. That is the top width. For the area, it is going to be B times Y using the shapes method, where we're breaking it up into a rectangle and then two triangles. It would be plus y times t times y. Now that can be generalized because y times t, this was when it was equal to 2. So let's just say that t is we've got a 1 to t, and so that means that here we've got a depth of y. So this is y here, and so if y is the vertical component, then this distance is going to be yt. Okay? So a triangle would be 1/2 of y times yt, and since we've got two triangles, that's why it's y times ty. So y is the vertical component of the triangle, ty is the top edge, and a triangle is usually half of those two, but we're putting the two together. So everyone feel good about this area formula? All right. The wetted perimeter, though, is a little bit ugly because we've got this, this bottom is easy. That's going to be in the wetted perimeter. Wetted perimeter for an open channel doesn't include the top where it's touching the air. The perimeter of a pipe is just the physical perimeter of the pipe because the pipe is full of water all the way to the top. And so for a pipe, the perimeter is just going to be pi d. But for this, we're only going to include where is the water touching. That's why it's sometimes it's just P that you'll see, but sometimes just to emphasize that it's only the wetted perimeter that we want to, P and PW are identical. Just this W is just like a little flourish that some texts add, and I get in the habit of doing it sometimes too, to indicate it's the perimeter that the water is touching the solid material, not the air. Up here it's air, and air isn't imparting resistance to the flow. Not very much anyway, a little bit, but not very much. So we ignore it when we're calculating the wetted perimeter. So there's going to be B as the bottom width, and that's easy. But then these sides, it's going to be the square root of y squared plus ty squared. Because y is the vertical component, ty or yt, depending on what order you write it in. That's the horizontal component of the triangle. So this distance is the square root of the sum of the squares. So P, wetted perimeter, is going to be the bottom width B plus 2 times the square root of y squared plus ty squared. And ty is in parentheses when we square it. We can further simplify that to b plus 2y, the square root of 1 plus t squared. So that's the formula for wetted perimeter of a trapezoid. And then hydraulic radius, r, is just the area divided by the wetted perimeter. And so if we combine those together, we've got by plus t y squared divided by b plus 2y square root of 1 plus t squared. Okay, so for your homework, they'll tell you a shear stress. You'll be able to calculate the slope of the energy grade line. And I think and they'll tell you the t value. They'll define the side slope of some channel. And I think what they're saying is, what is the depth that's causing this shear stress and this slope of the energy grade line? So you're going to be solving for y in that problem, if my memory serves me correctly. And so, y is in a lot of places, right? You can do a trial and error. You may be able to type the equation in your calculator and have it solve for y, or you can set up the equation in Excel and keep keying in lots of different values for y until it matches what you know is the hydraulic radius, and so on. Well, let's look at this diagram. We kind of had to rush through looking at this one last time. This is showing that as water is flowing downhill, here's the bottom of the stream, and it's got a certain slope, alpha. That's the bottom of our channel. If we do a force balance, there is a resistance to movement in the channel. That is the shear stress times the perimeter of the channel and the length that we're considering. So that is all of the shear force that's being applied to the fluid, and the other force that's relevant is the downward the component of the downward weight of the water that is normal to the channel. And so, why does water move downstream even though there's resistance? How is the water overcoming the resistance? It's because this h sub f, if it's in equilibrium, h sub f is equal to delta z. In every case where you have steady, uniform flow, the energy loss is the same as the delta z between 2 points. So in this case, the slope of the HGL, which is the water surface, this slope is equal to S naught, which is the channel slope. Because here we have an open channel where you can't have pressurized water in the same way that you can in a pipe. I mean, it's true that if we go into the water, there's a hydrostatic pressure, but you can't over-pressurize the flow beyond the hydrostatic equation like you can with the pipe. So here, the slope of the water surface, the slope of the channel, and the slope of the energy grade line, here where they have TEL, they mean total energy line. That's just another word, another phrase that means the same thing as EGL, energy grade line. You'll see it's the water surface, which is the HGL, plus the velocity head. So this dashed line, the total energy line, is the same thing as the EGL, which is what your previous textbook called it. We'll have all kinds of fun with trapezoidal geometry this semester. You're going to feel like you're back in a geometry class at certain points. Luckily, Excel simplifies things for us really a lot. When we're having to solve for the depth, it can get ugly, but Excel saves us plenty of times. Okay, so empirical flow resistance kind of started with the Chezy equation. And that's the idea that maybe there's some magic parameter that describes the roughness of a pipe or the roughness of a channel as water flows in contact with that. And the Chezy equation isn't used very much anymore. There may be occasionally you'll come across a reference that tells you a C value that's intended for the Chezy equation. But it was developed by looking at the relationship between flow velocity, the hydraulic radius, which would be knowing the cross-sectional area and the wetted perimeter, and the slope of the energy grade line, S sub f. And so through dimensional analysis and observation, it was determined that these C values could kind of predict what the flow velocity was going to be. And here are some C values for both English and SI units. We won't work any problems in class or homework or anywhere else we'll actually apply the Chezy equation. It's just more to address the history of empirical energy loss formulas and also show how they've developed over time. The Manning's equation, which we'll use a lot, especially in the open channel section of the course, is kind of an improvement on the Chezy equation. Velocity distribution is what arises when different areas of the flow field are different distances away from the surface that's imparting the resistance. And so what's on the screen here is a circular pipe being represented both with turbulent flow and laminar flow. And down at the bottom is one edge of the pipe. Here's one edge of the pipe, and here's the top of the pipe. And how do we know that the top of the pipe is up here? Well, it's because the velocity of the water when it's touching the pipe is 0. It has the same velocity as the pipe itself because it's a viscid fluid, meaning a fluid that has viscosity can't slip over another surface with there being no friction. The no-slip condition arises out of the acknowledgement that fluids do have viscosity. So the further away you are from either the top or the bottom of the pipe, in the center of the pipe, the flow velocity is the greatest. And if it's laminar flow, this distribution looks parabolic. When you have turbulent flow, on average, it will have this kind of a profile where this looks flat, but any given second, if we took a picture of the flow field right now, maybe it looks like this. And then a few seconds later, if you take a picture of the flow field, it might be in a completely different spot. But on average, it's going to have the shape that is depicted on the screen there. The faster the water is going, if you have a really high velocity, then this linear front will go further and further towards the edge of the pipe. So even this logarithmic shape is subject to change based on the flow velocities in question. Now, I've changed the title of this. I think it said velocity distribution on the slides that you've got. I retitled it today shear stress distribution because I think that that's a better title for what this is actually depicting. It's not depicting velocities. The last slide was, these are the velocities. But this is, if you look at the horizontal axis, that's actually shear stress. Okay, so at the top, this is the center of the pipe. It's not the other edge. When we were looking at this one, the top of the graph was, the top of the pipe and the bottom of the pipe. Okay, so in this one, this line represents the center line of the pipe that's the furthest away from the edge. So I'm talking about, what the center of the pipe means, right? It means that spot. Okay, that's that top line, and what you'll notice is that the shear stress is lowest at that location, at the center of the pipe. You have a couple of different velocities being depicted. This dashed line is saying this is what the shear stress profile looks like if it's laminar conditions, and then the other shear stress profile is if it's turbulent conditions. And so maybe what you could draw next to it is this is fast flow, and this is slow flow. Okay, so let's try and make sense of why is the shear stress profile like this when the water is moving through the pipe very fast? How do we interpret, and how would, like in a quiz or an exam, if I said explain this figure, explain why is the turbulent shear stress profile above the laminar one? Anyone want to take a stab at explaining that phenomenon? Fast velocity, and it looks like there's more shear stress at a certain point. The curve of it can be confusing. Just think about at a single location. This dashed line is, let's say, maybe, I don't know, 5 inches from the pipe wall. So if we're saying right here, this is where that dashed line is, but it's a cross-sectional view. So at a certain distance from the edge of the pipe, if you've got fast-moving water, then there's a lot of shear stress there. If you've got slow-moving water, then there's less shear stress. And so the magnitude of the shear stress, it's sort of reaching out into the flow. The faster the water is moving, the edges of the pipe, the influence of their resistance is felt deeper into the flow when the velocity is high. So in other words, if we look at the cross-section here on the screen, if the water is moving slowly, then maybe the shear stress is pretty high in this shaded region, but on the inside there's not much shear stress, and so the water is moving without too much resistance when the velocity is low. When the velocity is low, the shear stress isn't reaching out into the flow field as much. And that's part of the reason why in a low velocity we don't have very much head loss. Remember that H sub F, energy loss due to pipe friction, is FLV squared divided by D2G. So what this is a depiction of is saying if you have a low velocity, why is it that we don't have very much head loss due to pipe friction in low velocity? Well, it's because of the shear stress. The shear stress isn't reaching out into the fluid very deep, and the magnitude of it is lower than compared to velocity high. If it's velocity high, then maybe there's just a tiny little section where the fluid is able to move without a lot of influence from the resistance imparted by the pipe. So that's what those two different curves can be interpreted to mean. So can you distill all that down into 2 or 3 sentences for a quiz? I don't know. The boundary layer is that section it's shown here. There is, no matter how fast the water inside the center of the pipe is going, there is a section around the edge of the pipe that is laminar. Remember that right at the side of the pipe, the velocity of the flow is 0. So let's go back to when it was velocity low. So if it's velocity low, then that means that it's slow velocity in the center, but it's also really slow around the edge. And so there's some section of the pipe where in here the velocity is really slow. Or near the edge of the pipe, the velocity is really slow, and the Reynolds number in there might be less than 2,000 even. You could have laminar conditions in that boundary layer. The faster the water is going, then the boundary layer will get smaller. The boundary layer decreases as the velocity goes up. So fast velocity means you have a small laminar boundary layer. Slow velocity means that it's big. Here are some relative roughness values. This is copied out of a table that's in your book that says the relative roughness for different materials. And it's kind of interesting to think that they used to make pipes out of wood. Doesn't seem like it would be very watertight, does it? Just a metal band going around to keep all of the wood slats together. I guess it's similar to a barrel. You know, they can make barrels that don't leak. I guess they can make pipes that don't leak. But I don't know, when you put two sections together, you'd have to jam wadding in or something. It seems like it would leak. But the surprising thing about wood is if they're well made, the roughness is actually less than the roughness of cast iron. For example, if you look at this wood stave, a smooth wooden pipe is a lower roughness than cast iron and pretty close to galvanized iron. So they didn't necessarily have really horrible energy losses just because they were using wooden pipes back then. At the high side of metal pipes is corrugated metal, and that's like if you've seen the kind of corrugated metal pipes that they put under roads for culverts. They have really large corrugations, and it's not the metal itself that causes the high relative roughness there. It's the corrugations that they're measuring as having an equivalent height of 45 millimeters. Okay, back to the boundary layer. So we're just talking about how different metals have different roughness heights. So here, these little ridges are representing the grains, maybe in a cast iron pipe, or it could be the corrugations in a corrugated metal pipe. Whatever the material is, it has little bumps along the edge of it. You may have to zoom in really, really close to see the bumps, though, like in the case of a plastic pipe, where plastic pipes are really smooth. There is a criteria called the Morrison-Wigert criteria, and it's a way of calculating how thick is the boundary layer. And here's the formula for it. It's an empirical formula that says you take the shear velocity, and if you know the kinematic viscosity of the fluid, and so you can look up kinematic viscosity in the back of your book. It varies based on the fluid and based on the temperature of the liquid. You know, a typical kinematic viscosity for water is 1 × 10⁻⁶ meters squared per second. And if it's not room temperature water, then you just look it up from the table. What is the kinematic viscosity? But the Morrison-Wigert criteria is saying that you can calculate the thickness of the boundary layer according to this formula. Now, if you have calculated that boundary layer thickness, and it's more than 1.7 times the height of the roughness elements, then what we assume is that the laminar layer is so thick that it's completely submerging these roughness elements. And so this is called a smooth surface, a hydraulically smooth surface. So in a way, it's like the flow that's above this isn't even seeing those roughness elements because they're submerged in this layer that's laminar. And so you have very different hydraulic behavior if the laminar layer is completely submerging those roughness elements than compared to if the thickness of the laminar layer is less than 0.08 times the height of the roughness elements, epsilon. And that's it. Leaves a huge no man's land, doesn't it? You know, the first question you're thinking is, well, what about between 0.08 and 1.7? Well, that's a transition zone. But we can say that if that laminar layer is really small compared to the height of the roughness elements, then the peaks of the roughness elements are going to project into the turbulent zone. And so the water that's flowing past it is going to be very highly influenced by the roughness sticking out into the turbulent flow. The water that's above it, it's moving along without as much interference from the roughness elements as below when we have a hydraulically rough surface. Okay? So that's the Morrison-Wigert criteria and how the boundary layer interacts with the material that a pipe is made out of. All right. Well, let's apply some of these ideas. Here we've got the energy equation at the bottom, and the Darcy-Weisbach equation on the side. The Darcy-Weisbach equation says that you can calculate the head loss based on the friction factor, the length of the pipe, the velocity that's flowing through it, and the diameter of the pipe. In this case, we've got some elevated tank, and we need to find out where should we put the water surface. You know, how high should the tank be? Essentially, what is Z1? Because remember, with the energy equation, it's our notation to always have location 1, so it's P1, Z1, V1. Always have location 1 be upstream, and location 2 will be downstream in every case. And so here, we know the flow that should go through the pipe. The pipe should be 12,000 liters per minute. We know that at this location 2, which is at the top of the building, is going to be our location 2. We want the pressure at location 2. P2 should be 350 kPa. The length of the pipe that connects the tank and the building is 250 meters long. Here's the diameter. And rather than have you calculate the energy loss, the H sub F, it's just given in this problem that the frictional losses are 16.4 meters. And so you can substitute that directly into HL. As a reminder, there's two components to head loss. Head loss, H sub L, consists of the pipe friction, H sub F, which you calculate based on this formula, and H naught. And H naught are the local losses that are caused by pipe bends and flow-through fittings like a valve. And the way that you would calculate the magnitude of a local loss is K V squared divided by 2G. And each bend or valve or transition has its own K value assigned, to where, you know, a nice smooth bend like this maybe would have K of 0.4, and then a really rapid transition like this that's going to induce more turbulence might have a K value of 2.0. You can get those K values from tables in the text, or manufacturers of fittings will provide K values. In this case, they're saying, let's neglect the local losses between the reservoir and the building, and instead just assume that H sub F is equal to 16.4. So there's three steps that you should go through here. First of all, determine what water surface elevation is required at the tank. That'll just be as easy as solving the energy equation by substituting in all the known information. Solve for the friction factor based on the head loss that's defined. And then I'd like you to take a crack at the Morris and Wiggert criteria in calculating the thickness of the boundary layer. So I'm going to ask you to work on this one with a partner. If you're not sitting next to someone, scoot next to another group of students. So work through this, and then after I've given you some time to solve it, I'll put the solution up on the board. All right, let's review this from the beginning. So we set this up with the energy equation where we're going to use the open to the atmosphere top of the tank where the water surface is here as 1. Since the water in that tank isn't moving, or in reality maybe the water level is going down very, very slightly, we say V1 is 0 and P1 is 0 because the pressure of the water in this tank is the same as the pressure as the atmosphere that is touching. So P1 is 0, V1 is 0, but Z1 is the unknown we're trying to find. What we know about location 2 is the elevation above our vertical datum is 20 meters to the ground floor, and so Z2 is 20. P2 is the 350 kPa. We know we want there to be that pressure of water at the ground floor. And V2, we can calculate the velocity in the pipe at that location by the continuity equation. Over there, the Q divided by A, that's going to define the velocity at location 2. Head loss is given, 16.4 meters of energy loss between the tank and the bottom of that building. So just substituting it into the energy equation, we end up finding that the elevation of water in the tank above the datum, it should be at an elevation of 72.9 meters. And if it's higher than that, the pressure at the ground floor will be bigger. If it's lower than that, then the pressure at the ground floor would be less. Okay, so the next step is calculating the Darcy friction factor. And you know, this is just really a gimmick at this point in the example, because you'll never calculate the friction factor from a given h sub f. It'll always be the other way around. But that's just to get some experience implementing the equation. So when we do that, it is, if you rearrange the Darcy-Weisbach equation to solve for f rather than to solve for hf, then substitute in all the values, you end up with a roughness of 0.0194. Just to give you an idea of the typical range of roughness values, f values are usually between about 0.008 and 0.04. You know, that's kind of like the normal range. So if you're working on a problem and you're using an f value and it's like 32 or something, then you know you're really off the beaten path when you've got an f value that falls out of this range. There are, you know, like a really smooth glass pipe with low flow, maybe even lower than the 0.008. But generally, for typical pipes and typical flow conditions, that'll be the range of f values. So this one falls inside of that range nicely. It doesn't seem like things are messed up. Now the last thing was trying to get a try of calculating the thickness of the laminar sublayer using the Morrison-Wiggert criteria. And that's a multi-step process. The first thing is calculating S sub f, the slope of the energy grade line. So h sub f divided by L, and we find the slope of the energy grade line is 0.0656. Since this is a circular pipe that's flowing full, we can calculate the hydraulic radius just by dividing the given diameter by 4. And that gives us the hydraulic radius of 0.0625. And you'll notice it has units of meter, because we had, well, diameter divided by 4, or if you're doing hydraulic radius is area divided by perimeter. Area is meter squared and perimeter is meters. So that's why hydraulic radius has meters as its units. And last semester in fluid mechanics, I encouraged you to don't just write the numbers when you're solving a problem. And you'll notice every time I'm substituting numbers into a variable, I'm also substituting the units. If you continue that practice, I guarantee it'll save you some points either on a homework or a quiz or an exam. You'll always catch yourself making a mistake at some point in the semester if you take the time to always write the units. You know, like in this case, what if you weren't writing the units and for Q you just put in 12,000? Well, Q is 12,000, right? Well, it's more obvious that Q shouldn't be 12,000 if you write the units in there. If I had written liters per minute and then I looked, oh, area is meters squared, something's fishy. You know, so continue that habit. I think most people got in it last semester. So the shear stress, when we substitute in the hydraulic radius, the typical unit weight of 9810, we get the shear stress of 40 newtons per meter squared. From that, calculate the shear velocity as 0.2 meters per second. And finally, when you substitute it into the Morrison-Wiggert empirical equation, we get that the thickness of the layer is 5.8 times 10 to the minus 5th meters.